be modern and advanced. We want to be relevant, streamlined and efficient, objective, inclusive, and loyal. And if you ever think that we don't hold up to these values, please take us on. We've got a few committees. We're building quite a number of committees at the moment after we just started a few years ago, or just more than a year ago after closure for some time. So committees we have at the moment is the Inland Branch Committee. We've got the KwaZulu-Natal Branch Committee. We've got the Western Cape Branch Committee. We've got a Ready Mix Concrete Committee, a FIB Structural Concrete Committee, and a Cement Branch Committee. If you want to know more about what they do, just go and have a look on our website and you'll find some more information. Then also, we've got a special going on. Yes, just like any business in the world, we've got specials. It's special time. It's a half-year membership. It's now a half-year until the end of the membership. Membership ends end of February 2026. You can join now for half a year for exactly half the price. So a cost now, if you want to become a member for the next 6 months, is 750 Rand. And company members, you can join as Tanzanite, Emerald, Ruby, or Diamond. All these prices are half price at the moment. And we've got academic memberships. If you're an academic institution, you're not a member yet, please contact us and see how you can join. And then also associate members. Just who are our members at the moment? We've got Diamond members. We've got Creso and Quick Group. We've got Emerald members, the 6 companies listed on the screen now. Then we've got 2 screens of Tanzanite members. I'm not going to single anyone out. You can just see all their names. And Tanzanite members, the second screen, as you can see, is a number of people that's growing every week or every 2 weeks. We've got this session. Emerging enterprise members as well. We've got 2. And then we've got associate members, similar organizations like us, just different focus, and we work together with these people. And then our academic members, you can see there are 8 of them involved. Now, we've got this CONCRETEfix and CONCRETEclass webinars. Today is a CONCRETEfix, and why it's a CONCRETEfix is get your dosage or your fix of concrete knowledge of the most advanced and newest technology, research, practical implication, or practical products, or whatever. So it's really about the newest and the best and the latest in the industry and research. And future dates to keep in mind is on October 23rd, Willie Steenkamp will be speaking, and Jaco Kokart will be speaking on the 20th of November. And then Vandi Ulefi from AECOM will be speaking on the 19th of February next year. We've already got them lined up. The topics, exact topics, we're still finalizing. Then I said we've got the CONCRETEfix. We've also got the CONCRETEclass. The CONCRETeclass is where almost you're going back to university, back to college, back to your institution where you studied concrete technology or structural concrete. And we're working on the topics for the next one on the 9th of October. We've got a presenter lined up. We just have to finalize that. 9th of October. And then it'll be about concrete technology. We alternate 1 month between concrete technology and structural concrete design. So November again will be structural concrete design. Branch activities, keep in mind, look out for site visits, talks, concrete evening, careers in concrete evenings, and networking events. We're trying to put all together. And then CPD points, I've said in the previous 2 events, webinars, that we are behind. It's not really we behind as a concrete society. EXA was behind with all the approval of the CPD points. They are up to date now, and we got all of that, and we're up to date as well. So all your latest CPD points, your numbers you need for submission, you will find on our website. You'll find the link for that on our website. And if you struggle finding the link or not getting your information, please contact Natasha at the Concreteness Society. Further, have a look at our website for what we do, and then also LinkedIn. We're quite active in LinkedIn, so have a look, follow us, see what we do if you want to know about events and things happening in the future. So I always end off by saying the success of the society relies on the commitment and support of the individuals, companies, and stakeholders from the Cement and Concrete Institute industry. I mean, cement and concrete industry, meaning we need you guys to help us to help you, if I can put it like that. We thank you for your ongoing contribution. Okay. That's just a bit of marketing, advertising for the Concrete Society, enlightening about what we do. Today's presentation, we're very privileged to have from very far away, not on this continent, not even in this hemisphere. We've got Peter Taylor. He's the director of the National Concrete Pavement Technology Center and a research professor in the Department of Civil Construction and Environmental Engineering at Iowa State University. He spends time helping agencies and contractors implement best practices in concrete pavement design, concrete construction, and maintenance. His research is focused on developing sustainable mixtures that are engineered to meet the requirement of the environment that will be used, and developing test methods to prove that the mixture on site is going to survive and do its job. He's a professional engineer registered in Illinois and also active in a number of professional society. We're very privileged to have him here today to speak about impacts of vibration on concrete. So Peter, I'd like to hand over to you. Please share your slides.
All right, thanks very much,
And then it's over to you.
Great.
I just must mention just before end, we're going to have Peter speak. We must please not interrupt him while he's speaking, because it can get chaotic. But at the end, we'll have enough time for ample questions we can ask him. So thank you.
All right, great. Thanks very much, Billy. I was actually listening to the introduction there and talking about loyalty to the Concrete Society, and doing some sums in my head, and realized it's been 40 years since I've been involved in the Concrete Society of South Africa. I'm not that old, come on. Anyway, let's keep going. It's a real privilege to be able to present on this today. The caveat is that a lot of this is work or research that's ongoing. So that I have some ideas and some thoughts, probably raise some questions. And that's the whole intent of this presentation, is rather than us carrying on with life the way we've always done it, let's stop and think about why we're doing what we're doing, and maybe there's a better way to do it. So I need to acknowledge the assistance of Paul Jaworski. He's with Minich. They're a company that produces vibrating equipment. He's also chair of the ACI 309 Committee on Vibration. And some of the material that I have here are his images and materials extracted from his company and from a draft version of ACI 309 document. So let's climb into this. We've quite a lot of material to cover. I've got 40 odd slides in 30 odd minutes. So why do we do vibration? How do we do it? What does it do to the concrete? What are some of the best practices, the recommendations that are current, coming from the past, and maybe what we need to think about changing? And then the final couple of slides are going to be, what about the mixture? Can we make vibration-proof concrete as opposed to making changing our practices to survive the vibration that we're putting into it? So a very quick image here I tend to use just to sort of the total overview of the things we need to pay attention to when we are building with concrete. And again, I need to emphasize this: the institution I work for is entirely focused on pavements, but I think a lot of what we talk about, the thought processes still roll over into almost any concrete application, running from RCC through bridge decks, structural concrete, I think we can make them all apply here. But we start off the process looking at the performance of what do we need, what is the strength, which every structural engineer lives and dies by, but what's the durability requirements? What are the levers that we can pull to get there? And then we need to do some measuring. Can we be sure that the mixture is going to deliver the performance we're looking about? And that's been the focus of the performance engineered mixtures program that I've been heading up for the last 15 years. Then the batching, making the concrete, the quality control, making sure we've got the right amount of water and air in the concrete. And yes, I know you don't need air, but it's a big issue in our lives. Right now, today, it is 18 degrees, cloudy and beautiful as we head into fall. You guys are warming up and heading into spring. And you haven't had any freeze-thaw cycles. We're heading into a lot of them. Transport, moving the concrete around and placing it. The concrete that's delivered, is it the same as that which we need in the specification? Once it's been dumped, what do we do to the concrete to move it around, get it into the forms, get it out the back of the machine? And a key part of that is vibration. And we're starting to learn that vibration is essential, but if not done properly, can be detrimental. And so we have to pay attention to that. And that's where the focus of today's talk. Then there's the finishing, putting the surface on the concrete, curing, sawing. Another focus of what we're looking at the moment is the finishing activities. Again, with changing cement chemistries, we're finding that finishing crews are really struggling to understand how and when to do their finishing work. I've had an example recently of a slab that was placed in August in the heat of summer. It had failed. We'd lost the complete surface of the slab before October, before we'd even had the first freeze-thaw cycle, or before we'd put the salt on it for the first time. So it's not cold weather related. It was constructability and construction practices related. So that's another hot topic that's keeping us awake at night right at the moment. So, and again, this is the whole picture. We're going to be focusing on the bottom middle for today's discussion. All right, so why do we vibrate? Well, the obvious answer is to consolidate it, to get the big bubbles out of the concrete. We often see it on construction sites. This is the best photo I found. It doesn't have a vibrator in it, but there's also always the need to move the concrete from where it's dumped out to the place where we want it to be at the end of the day. And it is common to use a vibrator to do that. Don't. It's not good for the concrete. And this is not new. It's been in every book that I've been involved in writing, from design and control, Fulton's, and the IMCP manual. All of these publications say don't do it. So yeah, I know everybody does it. Don't do it. We also use vibration to help bring a little cream to the surface so that the finishing crew has something to work with. Now, sometimes the mixture is so bad it's beyond redemption. This photograph is from a test section we were building with a non-traditional cementitious system, and the delivery time was 40 minutes, and the admixtures had given up the ghost and left the mixture within 10 to 15 minutes of batching. And so what was delivered was a brick, and the crew could not do anything with this, regardless of how much vibration they put into it, how much floating they did to it. In the end, after about half an hour, they gave up, moved on, and within a couple of hours, this was in the back of a dump truck being hauled away for disposal. So again, the mixture can have implications on what vibration we need to be doing on the system. This was an extreme example. How do we do vibration? There's all sorts of tools that we can use. Here we have two different poker vibrators, a nice hearty, chewy 50, 75 millimeter poker vibrator. Great. Here's another little dinky one that I saw on a construction site earlier this year. I actually looked up the specifications of this machine. You can just see it up here. It's a handheld. It's got a 25 millimeter head. It runs at 12,000 VPM, which is absurdly high. And the sphere of influence is 100 millimeters, which is also pretty low. the interesting thing about this is that this gentleman was moving the poker about a meter every time he dropped it into the concrete. So, you know, the sphere of influence is this much, and he was spacing it this much. Was it doing any good at all? Probably not. The other thing is that he had it in the concrete for less than a second. Again, was there sufficient time for it to do any work? No. So was it a waste of time? Yeah. Is there a better way to do it? Yeah. Obviously, he'd never had any training. All he was told is dip it in the concrete occasionally. And that's exactly what he was doing. We need to help people like this with here's the way it should be done. Yeah, and I know I'm a professor, I'm a lab rat, but it's important for us to get the theory and the best practices into the hands of the people on the construction site. Next up are the gang vibrators. Here we have a beautiful, I think it's a 9-meter machine with a whole bunch of nice, thick, chewy, high energy vibrators, hydraulically driven and monitored by a sensor system built into the vibrators. And this screen is mounted on the side of the machine. The key part of this is that by using these sensors, you can tell whether or not all the vibrators are running. And are they running at about the right speed? If you look carefully at the numbers, which you probably can't see, they're all running at about 8,000 VPM. Pretty good setup. Somewhere in my slide deck, I have an image where the hydraulics had failed on one half of the machine, and the other half they were still running. And there was a very clear difference in how the concrete looked into the machine due to the action of these vibrators. And I spent 2 days searching for it, and I couldn't find it. I'll probably come across it later on this afternoon. Okay, then there is the Boer Plan version. This actually comes off a roadway in Gauteng, which I was visiting with Brian Perry probably about 10 years ago. Really cool stuff. This is great stuff. It was perfect for the application. You know, one of the big things that's different between American practice and South African practice, here in the USA, people are expensive and machines are cheap. The exact opposite happens where you are. So this sort of setup where cheap machines and a couple of people to move it around, that's a cool answer. Great. All right. Another tool is the vibrating screed. And again, I've got 2 different extreme examples here. This is that same site I was showing you before. There's the same gentleman. Here we've got another guy operating a screed vibrator, which is basically a beam with a lawnmower engine, probably a 2-horse, 1 kilowatt machine mounted on it. And this thing is jumping up and down a little bit. Again, is it doing much good? Well, it's certainly bringing cream to the surface. Is it vibrating the bottom of that 100 millimeter slab? Probably not. But yeah, at least we're getting a surface on it. The other extreme is this nice, big, chewy machine built on a bridge, quite a lot of fairly heavy weights on it that you can see along this shaft. A fairly large, again, lawnmower engine on it. My catch with this one is that look at the beam. The ends of it are riding on the old concrete or the forms. So that means the bulk of the energy is simply bouncing the machine up and down on hardened concrete. How much energy is actually going into the fresh concrete that we're trying to work with? I don't know, not a lot. So again, think a little bit about what are we trying to do here, and is the equipment we're using achieving that end? In both of these cases, all right, and then finally we have the vibrating roller. Again, how much energy is getting into this thing, how far the field of effect is. Now, again, this is very narrow, thin slabs, probably only 75 millimeters. That's doing a good enough job. We can live with that. The smart version of the vibrating roller is the laser screed, which is, again, an expensive machine and one operator. And it's laser controlled, tied to a pre-programmed GPS system. So all he has to do is say go, and this machine moves the arm backwards and forwards, does the roller placement. It's not a great image. This was actually taken on a construction site opposite my office last week, and We weren't allowed on the site. We were just peeking through the fence and trying to poke the camera through the gaps in the fence. And yeah, not a great image, but it does illustrate what you can use. And then there are form vibrators. I'm not going to talk about those. Again, they only affect the surface closest to the form. How much energy comes through these things? Do they do a good enough job? The primary issue, the primary application of these that I've seen is in tunnel forms, because there is no access to any other form of vibration. And they have some application right there. I'm not going to talk about those any further. So now some theory. What happens when you put a vibrator into concrete? Here we have a poker, a shaft coming in from above, either electrically driven or hydraulically oil driven. What it does is that there's a heavy weight, offset weight, eccentric weight inside there, and it is rotating horizontally. So it's pushing out waves, sideways, P waves, pressure waves, as this thing rotates horizontally. So what? Well, let's go and do a little bit. I've got 2 slides of rheology discussion. There are 2 parameters that we worry about in rheology. There is the yield stress, which is the amount of energy it takes to start moving the concrete. How strong does the worker have to be to pick up the concrete with his shovel? On the horizontal axis is viscosity. How much effort does it take to keep the concrete moving and or make it move a little bit faster? All right. And again, I'm a dumb engineer. These are all fancy terms with exotic units. What does it actually mean? Well, let's make it simple. Water has a low viscosity and a low yield stress. It fills the shape of the little glass that it's in very readily. That's why we have waterfalls and pretty rivers. Right. On the other extreme is regular concrete. It has a high viscosity and a high yield stress. It takes a lot of energy to move it, and it takes even more energy to make it move even faster. Fill up the other corner is honey. You've all got at home the little containers of a honey pot shaped like a bear. And honey works in those containers because it has a low yield stress. It'll keep moving, but the viscosity is high, meaning it'll move slowly. And that's why we also have to have fancy dippers rather than spoons to get the honey out and onto your toast. All right, in the middle, self-consolidating concrete, very low yield stress. And that's by definition, we want concrete that flows under its own weight. But it does it slowly because it has a relatively high viscosity. How many hours have you spent waiting for the flow test to finish? I couldn't find anything that fits this other corner, so we will move on. Having defined those terms, when I talk to people who are experts in rheology and say, I want to apply these technologies or concept to concrete, they'll laugh at me because rheology is the study of fluids, and this stuff is no way a fluid, except when you put energy into it or when you change the chemistry of the system. So the same axes, we're at a data point for a given piece of concrete. If we put superplasticizer into it, it lowers the yield stress predominantly with some small effect on the viscosity. If we put water in, it also lowers the yield stress. Water is a lot cheaper than superplasticizer, and that's why every ready-mix truck that arrives on site, the supervisor says, add 40 liters before he even looks up from his newspaper. And not good practice, but very common. Air changes viscosity, but not yield stress. Silica fume changes viscosity, but it makes the yield stress go up. It stiffens the system up at higher dosages. What happens if we put a vibrator into this concrete? Conventional wisdom is that it has a significant effect of dropping the yield stress. And a lot of the theory, a lot of the teaching has been based around that assumption. That's not a bad assumption, but based on what I'm going to be presenting in a few minutes, I would also argue that it has some effect on the viscosity. It's not a straight up and down. It's more likely to be following the line of the superplasticizers. Okay, so vibrator reduces yield stress. So we put a shaft in, it vibrates, it oscillates. What does it do to the yield stress? Reduces it, which means that air bubbles can float up because there is less yield stress slowing them down, preventing them from moving through this very stiff mixture. The conventional wisdom at present is that the amount of energy we need to be putting into there, expressed in units of gravity or acceleration, is about 3g. Has that been finalized? Maybe not. Water moves horizontally, and I'll justify that position. This is a relatively new thought, but it has fairly significant impacts on what we should be doing on our construction sites. It also causes the aggregates to wobble as it's being vibrated. I had a photograph where somebody had placed concrete with angular aggregates, not angular, but misshaped aggregates that were long, flat, and thin. And in the photograph, all of them are horizontal. And that can't be because they'd been, during the mixer, they would have been random. But once they'd been vibrated, they'd all rotated under the action of the vibrator, and they were all sitting completely flat. Another hunt from my photograph system. They can also sink, and we have segregation, is that as the yield stress of the system drops, the heavy particles sink, the light particles go up. And again, we're deliberately doing that because we want the excess or the high-sized air bubbles to float up and get out of our concrete because we want a nice, dense, well-consolidated system. But at the same time, the coarse aggregate particles can sink depending on the gradation, the fines content of the mixture. All right, not a great image. I cut and paste this out of one of Paul's PowerPoints. But we need to also think about how much influence does a given vibrator have. Early on, I indicated there was a 75 millimeter head and another guy with a little 25 millimeter head. The 25 millimeter head is reported in the manufacturer's guidance that it has a 100 millimeter influence. That 75 one is probably closer to, I'm going to forget my units, 200 millimeter sphere of influence, maybe 300. That radius depends on the amplitude of the device, and that's controlled by how much offset there is on that heavy weight. It's the frequency, the size of the weight, and there's also impacts of the mixture. So it's not, again, as engineers, we like simple rules of thumb. My challenge is to say it's not just 200 millimeters. It will vary depending on all of these parameters in front of us. The fall off, is it linear, logarithmic, or some other model? We're still working on that. I suspect it's logarithmic. So the closer you get, the more and more influence you see. But yeah, we'll probably report that in a year or two when we get the work wrapped up. So the impact, it moves air, and this is good. We get the big bubbles out of the concrete because these don't do anything for us. They reduce the strength, they increase permeability. How much is bad and how much is good? Also a topic of debate. Whenever I go to Australia and present there and I show a photograph like this, which is a fairly typical image of a core from a roadway, and they're having quiet hysterics because the specification in Australia is that the density of the concrete in place has to be 98% or more of the theoretical maximum. And I suspect that this one does not comply. Do we have a problem with that? This core came from a perfectly well-performing concrete. It was actually the companion for a bad one. So this was the control good one. And this concrete's performing fine. So is 98% the right number? I don't know. More work needed. We've got to figure that one out. But we are also moving, some of the bubbles out, if not most of them. And again, how long do we wait to get all of these bubbles out of the concrete? That's part of the question. Do we remove good air? That's a point of discussion. It's fairly traditional for us to say, don't over vibrate it because we're going to beat out the good air. Maybe. And here's the justification for that. moving air can be modeled using Stokes' law. Now, Stokes' law simply describes mathematically how fast a bubble will float up in a fluid. So tonight, when you're sitting on your stoep, drinking your soda water, just watch it and you'll see the big bubbles float up pretty quickly and the little bubbles take their time, gently wandering up the side of the glass. And that's exactly modeled by this equation. Now I've got a chart of some number crunching that we did, and I very deliberately didn't put the numbers in the x-axis because they're not right. But the shape of the curve does illustrate. It's logarithmic, or a power curve, that a big bubble will go up out of the concrete relatively quickly. Traditionally, again, when I've been on construction sites, the operator, if he's well trained, doing things properly, we're probably looking at about 15 to 20 seconds before the big bubbles stop rising to the surface. We're good to go. Next, move to the next location. So this one still needs calibration, but look at the variables in here. The velocity is a function of the difference in densities of the liquids, whether it's air, concrete minus air. Gravity, okay, that's fixed. The radius of the bubble as a square. And nu, that's the viscosity. That's that horizontal axis in the charts that I was showing you a little bit earlier. So the lower the viscosity, the faster the bubbles will go. The higher the viscosity, the slower they will run. And that's why I'm also thinking that chart, viscosity has an important part on the impact of vibration, because again, we're vibrating to get the bubbles out and the big ones. So some work that we did some time ago, and we're actually repeating and enhancing, filling up some of the unknowns, is an exercise we did where we had, I think it was a 120 millimeter long, 100 millimeter wide. I gotta get another units are in the next image. But it was a wooden box with some rods of different lengths. And I'm going to come back to imperial units because it's too early in the morning for me. This rod that you can see here was 9 inches. Underneath was a 6-inch rod, and below that was a 3-inch. So 75, 100, and 125. And sensors connected by magnets to each of the ends of those rods, tied to a device that measures the amount of energy being received by that sensor. And what we were looking to do is to see how the mixture variable impacts how much energy is received at the tips of each of these rods. So the rods are there just to transfer energy to the sensor. Fill it up. You can see it was a 25 millimeter head poked in vertically into this space. So here's the dimensions, just a schematic of what the box looked like. We then let the concrete harden and pulled cores, cut the cores into slices, and we also cut them vertically, and we did air void analysis on each of those slices. And what we showed was that right next to the tip of the vibrator was the least amount of air. Furthest away and at the surface of the vibrator, the air was higher. So there's certainly a trend of moving air away from the vibrator. Now, again, following that model that I had a little earlier, I'm beginning to think that, again, it's a power curve, that it's very effective at moving big bubbles. How big is big? Typically, we say 1 millimeter is about the limit of the difference between a bad and a good air bubble. So getting all the big ones out relatively quickly, vibration does just that. Okay, I'm not going to harp on the air void system too much because you don't care. This is the one that's really interesting. This is where you pay attention for the next 3 minutes. It also moves water. What? Yes. Vibration moves water, and it moves it horizontally. This is a very simple but efficiently demonstrating toy that Tyler Lay from Oklahoma State University did. He took a standard bucket and he punched little holes in it. I think they were 4 mm, all over the place, all over this bucket. He then stuck a poker vibrator into the middle of the concrete, and you can see water, paste, fluid flowing out of this bucket. And I've got videos. I was reluctant to try and put videos into this presentation because I know teens hates videos. But you can see all of these holes have water pouring out of them. This is a vibrator running at 12,000 VPM. He then replaced the concrete, or I think he did the opposite way around, but he did the same exercise at 6,000 VPM. There wasn't any water coming out. Aha! Slowing the vibrator down reduces how much water or how fast the water is moved through the concrete horizontally. So what? Big whoop. Well, here's why. How often have you stared at a wall with pretty bad honeycombing at the bottom of the wall? How often have you fooled around with the sand content of the mixture? How often have you fooled around with the water reducer and the super plasticizer, or even tried viscosity modifying admixtures or rheology modifying admixtures to try and prevent just this? I've been there. I've stood in many walls and stared at them and wondered, I wonder what went wrong. Well, here's what went wrong. The vibrator was running too fast. That's a new thought, but it's real. All right, here's another exercise. Contractor had to do test sections, big project, and they had very tight limitations on what the off-the-shutter finish had to look like. Same concrete, same day, same types of forms, same operating crew. Vibrator running at 12,000, all sorts of distress. Vibrator running at 6,000, beautiful concrete. Couple of little bug holes, but none of this ugly stuff on the surface. We've got some cores in the lab at the moment. They punched cores through these things. We've measured resistivity and we didn't see much difference in the bulk resistivity through the concrete. I'm going to be picking up the cores tomorrow from Minneapolis, and we're going to be doing another little test to see if we can pick up the permeability at the surface. And I'll show you what the test looks like in a little bit. So again, a couple of weeks' time, we should have some interesting data. This test I stole from a petrographer friend. You drop 2 microliters, very small drops, onto a dry surface. If it's a cracked specimen or a sawn specimen, you try and avoid dropping it on the aggregate. You drop it on the paste or the mortar. And you start a stopwatch and you wait for how long does it take for the droplet to be absorbed into the concrete. It's entirely subjective. It's a terrible test. I'll never get it past ASTM, but it's really good for telling us the surface of the concrete is different from the heart of the concrete. And we've demonstrated that very, very, very clearly often. We did that same test. Remember that box with the vibrator and 3 rods and the cores that we pulled out? We did this test, the drop test, again on those same cores. And what we found is the absorption time next to the tip of the vibrator was high. The absorption time at the far corner from the vibrator was low. That tells me the water has moved both up and horizontally from the tip of the vibrator. So the vibrator is moving moving the water away from the tip of the machine. This is, again, a new thought. All right, so vibrators move. Air up, water sideways. What does it do to the aggregates? This is a classic example from a highway near where I live. It was a really ugly mix. It was very crunchy. The workability was awful. And the contractor's response was to accelerate his vibrators as high as they would go in order to get the concrete through the paving machine. And here we see, right where the vibrator was running, a whole lot of mortar, and all the aggregate has been pushed aside. Between the vibrators, it looks a whole lot better. What's interesting is that right now, the road is still there. It has survived, but there are horizontal stripes every 18 inches. Somebody did a conversion for me. 450 millimeters. There is a stripe where the vibrators had run. We call them vibrator trails. And I drive, every time I go to the airport, I drive along this road and I rumble. Here's an example from, on the right-hand side, an example from an airfield. Not a great mix design because it had way too much mortar and not enough coarse aggregate in it. It was over-vibrated, and you can see the top 50 millimeters of this concrete has no coarse aggregate. This is an airfield. It's going to be landing C-150s and jumbo jets on it. How long is it going to last? No, it's not great. So again, this is the combination, over-vibration and a lousy mixture. We need to pay attention to both. We need a mixture that will survive vibration. We need vibration practices that don't kill the mixture. All right. So what can go wrong? Too little vibration, you don't get all the big bubbles up. Too much vibration, you get walls that look like that. And again, we've all seen them. So this is one of the ones that is being pushed through ACI right at the moment. This is a table on the left-hand side of how much energy you will get out of vibrators at different sizes at different speeds. And you can see if you've got a relatively small head, you'll at 11,000 VPM, you'll get the same energy as a big head at 6,000 VPM. Now again, high frequency will move water and that's bad. Low frequency doesn't move water, and that's good. So if you have a choice, put a bigger head into your concrete. There's also guidance in C309 of, the radius of influence is a function of the size of the head. The bigger the head, the greater the size of the sphere of influence. And now again, this table doesn't take into account the mixture. But okay, we're engineers, we like tables, we like rules of thumb. This is as good as we're going to get. I suspect it's going to be changed in the new version of ACI 309. Paul sent me the latest version yesterday, but he forgot to include this chapter. So his apology email with the new chapter arrived after we logged into this webinar. So I don't have it. Well, I have it, but I didn't get it in time to be able to show you. All right. So then the guidance goes to, I was whining about the crew that weren't properly trained right at the beginning. One of the things you need to teach them, put it in vertically. Don't do this game of different angles. Put it in close enough together. Know the sphere of influence for the concrete that you are working with. And you can often see that. Put it in, and very quickly you see paste rising to the surface. What's the diameter of that sphere? Put the next poker in just about where that one ends. And so you get plenty of overlap between these, maybe 1.5 times the difference. Make sure you're getting enough energy. Here we have a slab on grade where the top is well vibrated, the bottom is less so. Does it matter? Probably not, because this is daily practice and we're not seeing a whole lot of distress. But we need to worry about the zone of influence. We need to worry about the overlap. We need to worry about uniformity of our practice because, if it doesn't get vibrated, that's not great. We need to worry about how much energy is arriving through or being distributed. This was from that box exercise. We measured the vibration energy for a 25 millimeter slump and a 100 millimeter slump with similar air contents. And what we found is that the amount of energy being transmitted was way lower through the low slump mixture. And that's reasonable because if you've got a stiff mixture, it's going to absorb that energy rather than transmit it. Water transmits energy very readily. Dry materials are going to wobble, and so they absorb that energy. All right, here is similar exercise, more recent data. This is a limestone aggregate. This is a gravel aggregate. And again, a lot of difference. I was kind of expecting to see more variation between these two. But yeah, the type of aggregate, whether it's rounded or crushed and angular, can make a difference, although it's not huge. When do you stop vibrating? Rule of thumb has always been until the bubbles stop appearing. That's pretty subjective. The 309 guidance coming up is around about 1.5 to 3 seconds. In a vertical application, if you're running in a paving machine and running horizontally, 10 to 20 seconds per cubic foot. Yeah, we'll have to do the conversion for you. Do we need to tie it to the paver speed? Yes. Can modern pavers do that? Yes. Have all of them done it? No. Have we figured out how to tie it together? What are the parameters, the on-off switches we need to do? We don't know yet. We will be building an airfield runway in Charlotte probably early next year. And we're going to be doing tests where we're going to be running the paver fast and the vibrator slow, and the paver slow and the vibrator fast. What if we stop the vibrator or stop the paver, and we stop? If we do or do not stop the vibrators, we're going to build cores out of that. We're going to be looking at the surfaces. This is part of $1 million project, or $1.5 million project that I'm helping to manage. A year from now, 2 years from now, we should have some really great data on that practice. Do admixtures and water behave the same? No. And again, this is ongoing work. I don't have any firm guidance right at the moment, but I have students in the lab today doing some of this work. All right. What about the gradation of the aggregates? Yes, I know I've got 1 minute and I've got about 3 slides, so we're in pretty good shape. Here is a mixture placed by a contractor, 1-4. And you can see lots of surface bug holes. He was really struggling to make a great surface on this concrete. They contacted me. We fooled around with the gradation of the aggregate system. We didn't change the aggregates. We just changed the ratios of the coarse, the intermediate, and the fine. We actually took out 50 kilograms or about 40 kilograms of cement. And this was the following spring. Beautiful. Saved him money, made better concrete. We also tuned the vibrator system on the system. So again, paying attention to the mixture and the vibrator system, slowed the vibrators down. He was getting better concrete at the end of the day. So how do we measure this in the lab? This is a little toy we've been developing. It's called the V Kelly. It's based on the original Kelly ball, which was used to measure slump by measuring how far a hemispherical ball or hemisphere falls into the concrete under its own weight. I bolted a vibrator to it, and what we found is that the rate that the ball sinks at by square root of time is pretty linear. We have an ASHTO test method to be able to define how to do this test. Does it work? Yes, we did. This is some work from Minnesota where we had different mixtures running through the same paving machine on the same day. We measured the V Kelly of every 4th or 5th truck as it came through. This was a V Kelly that had a 0.6, which is about a pretty good number, and you can see the surface of the concrete. This one, visually, it looked great. The slump of both of these mixtures was the same, but the V Kelly was a lower number, implying that the mixture was less responsive to vibration, and that's exactly what we're looking for to model what's happening inside a paving machine. And sure enough, as it came out of the back of the machine, it wasn't pretty. So again, the tool is useful for identifying, can we get a surface on it? Can we get a finish on it for the same slump? So we're trying to figure out the effects of admixtures, different type of admixtures compared to water. We're trying to understand better the effects of water and the effects on water and air. We're understanding effects of paver speed. That's the FAA project. We're trying to install better monitors on the pavement. The thought process being, put a pole, a bit like that box, horizontally in between the vibrators inside the paving machine and see how it responds to the energy coming from the vibrators that it is in between. Can we correlate that to the quality of the mixture being delivered. So then we can start automating this thing. Is that if this sensor is saying, I hate the mix, the sensor can phone the batch plant computer and say, fix it, rather than having the site supervisor calling the batch plant operator and making comments about his mother. It becomes automated. Personal relationships are very well improved. All right. The other thing we're doing, the V Kelly as it stands with the small head only works up to about a 75 millimeter slump. We're just getting started on putting a bigger head on it and seeing how it works with structural concrete. We've done one test and it's looking pretty promising. So that means for structural concrete, bridge decks, walls, columns, can we get similar information? Is the mixture going to respond well to vibration? Can we get it fully consolidated? And again, I can control the frequency of this device, and we can also pick up the effects of moving water, moving air. So a lot of questions, a lot of thought-provoking thoughts, I hope. Billy, I'll give it back to you and invite some discussion.
All right, thank you very much. And we can give him a round of applause. There's a react button at the top of your Teams if you don't know it. There you can give a reaction. See, there's your applause coming.
Thank you.
Thank you very much for that really interesting and thought-provoking, and I'm sure that it created a lot of questions. And I would open the floor for questions now. Just raise your hand so we can do it in an orderly fashion. Our first person is Grant Hardley. Yes, go ahead.
Thanks, Peter. Thanks, Billy. Yeah, very interesting presentation. I've got a whole bunch of questions, but I want to give other people a chance. Okay, so I'll maybe limit it to two. Have you ever used self-compacting concrete in the pavement work that you've done? That's the first question. And then the second question is, how should we adjust our mix designs to account for possibly expected poor quality control on site?
How much time have we got? We need an hour. Okay, first of all, Grant, SCC in pavements. Yes, I personally, well, I was part of the team that was fooling around with it. It was being led by Kejin Wang, a professor here at Iowa State University. It still had a relatively high slump. It was about an 2-inch slump, but it was so packed full with admixtures that it would keep moving. And we actually built a sidewalk and a city street without putting any consolidation into the mixture. The sidewalk is still there. The roadway failed miserably within one season, but it turned out it wasn't the concrete. It was because the contractor hadn't done any foundation work, because the test section right next to it also failed miserably. So after about 2 years, the city came back in and put in asphalt, which is truly horrific. But yeah, it has been done. It didn't find a lot of traction. The biggest concern was that with this material, it's a real struggle to keep a crown. And we need that for drainage. So I'm not sure that it went anywhere. It definitely didn't get too much traction. I'm not sure that it's going to be resurrected. The other question is making idiot-proof concrete. Yeah, working hard at, again, the parameters that we're looking at is, let's fool with it in the lab and understand what are the effects of over vibration, insufficient vibration, or bad curing, bad weather. The caveat with that is that, yeah, we can make concrete that's, I remember Rod Butler from the CNCI lab 40 years ago used to tell me, concrete is really abuser friendly. And we can make it so. The only problem is that now, as we're pushing carbon contents lower, as we're incorporating all sorts of interesting new cementitious materials, what we're finding is that it's actually becoming more sensitive to bad workmanship. and that seems to be the tension is we can make really good concrete with current material or innovative materials, but quality control does have to be better. So if you're really worried about quality control, yeah, then we may have to go back to old-fashioned mixtures and materials. That's an interesting tension and one we haven't figured out how to solve yet.
All right, thank you. Thank you for those questions. I've got the next question from, I'm not sure how to pronounce the name, Ouya. Nathaniel.
Thank you very much. Thank you, Peter, for such a wonderful presentation on concrete. It's amazing. My question is, I'd like to know, with the modern technologies coming up in construction, like the 3D printing, well, seen in Canada, where larger devices are used to extrude large amounts of concrete and used to build structures. So now we're having more exposure to air. Is there a potential? Are we going to be seeing more bleeding in the concrete? Are there going to be more spaces with this new technology, or is the concrete going to be better than what we're having already? I'd like to know.
That's another hour-long lecture, but the short answer is, yeah, 3D printed concrete tends to be very small aggregate, if any coarse aggregate, because it's being extruded out a relatively small nozzle. It has a very high yield stress and fairly high viscosity. And that's the art of designing a good 3D printed concrete. It is never vibrated. So again, the art is preparing a mixture where you don't get a lot of entrapped air, and getting it to stay in place. And again, my department has just bought a full-size 3D printer. It's about the size of the room I'm in, and we're just getting started on setting it up and getting to understand it. But yeah, vibration and 3D printing are disconnected. I forgot the second part of your question.
So the second part is finding, will this 3D printed concrete be much better than the traditional concrete mix we're having?
Right. Define better. Because it doesn't have coarse aggregate in it, paste contents are relatively high. So from a carbon point of view, it's poor. From a time point of view, it seems to be better, although again, I go back to my discussions we used to have with Brian Addis, was that, concrete shrinks. And so, if you want to do rapid construction with a high paste content concrete, are these things going to crack at the corners? Quite possibly. Can you make it strong enough? Yeah. Can you make it able to resist the environment? Yeah. And that's the discussion. The Corps of Engineers are the leaders in this country of doing research on 3D printing because they want to do it in a hurry and everything else doesn't matter. So yeah, can it be better? Depends what you mean.
Thank you, Peter. Thank you.
Sorry, my microphone was switched off. My apologies. Yazdi Mohammed Ali.
Hello, thank you very much for your very interesting presentation. I have two questions. One is related to the new cementitious materials that you mentioned and is very important. I was wondering if you ever investigated, for example, the more slag in the system, like let's say more than 50%, and the relation with the vibration, and if this is ever investigated. And the second question was vibration in relation to bleeding, water bleeding. Is there anything, or did you investigate that? And do you have any comments on that? Thank you.
Yeah, good questions. Slag and bleeding. Yeah, I think slag probably has a slightly negative effect on the amount of bleeding. We haven't looked at it as a parameter for the vibration work we're doing. It is planned, but we haven't done it yet. So watch this space, or maybe I come back in a year and we have a refresher on what we've learned in the interim, assuming I can get my students to be productive. The other one was, sorry, it's too early in the morning. Yazdi, what was the second part?
Yeah, the second one is basically the bleeding water, because you mentioned a slump, and I'm just wondering, is there any relation, because the amount of water that is in the mixer and the how long you vibrate, and then the effect, is there any correlation there, or do you have any remarks or any suggestions in that case?
Yeah, I have a suspicion that the amount of water that's moved under vibration is strongly tied to bleeding. In fact, Paul Jaworski will say that often in his presentations. Again, we haven't investigated it yet. Hopefully I can find the resources to do that work. But yeah, I think you're right. I think it does have a tie together. Now, again, think about what controls bleeding. It's primarily the amount of very fine material, either the dust in the aggregates or the amount of cementitious materials you have in the paste. So, and there's also an admixture effect. So supers will tend to bleed a little bit more. So again, that's a nice complex issue that we have to figure out how to investigate, explain, and design for going forward. So more research needed.
Thank you.
Excellent. Thank you. I think we've got time for one or maybe two questions. Is there anybody that would dare a question?
I think one just came in the chat.
So I didn't see. Grant has got a question, but before we go to Grant to really ask his question, let's just check the chat. Has effect or efficiency of release oils on formwork and molds been evaluated with regards to releasing air bubbles from closed insides, leaving smooth off-shutter finishes?
Really good question, and I don't know the answer. That's the definition of a good question, right? Yeah, that's a good thought. Something we need to investigate. I fooled around with Zendrain. It was a permeable foam liner when I was based at Midrand many years ago, and that worked really well. It was fiendishly expensive, but it gave us great finishes because it was absorbing all of that excess water out the surface. The effects of oils, yeah, that's a whole nother world I haven't looked at all. Again, I work in pavements, so we don't have forms, so I'd have to find some money to fool with that.
All right, thank you, Jeffrey. And then Grant, you can end off with a nice question.
Thanks, Willie. It's more of a comment, but I'd like you to comment on the comment. Is that I've always been told that the risks of under vibrating are much higher than the risks of over vibrating. So we should be a lot less strict about over vibration than under vibration, because the under vibration happens more frequently and the effects of that are far worse. Would you tend to agree with that? I know it's a very general, broad question, but is that a fair assumption or statement?
In general, yeah, I think I would agree. It may depend on the application, but yeah, I'd rather have really well consolidated concrete at the bottom of the form where the tensile stresses are than under vibrated concrete.
Okay, thank you.
Thank you. And Grant, one final question. You had a number they listed earlier.
Okay,
let me go.
If you'll entertain me, thank you. It kind of follows on the previous question that was in the chat. What can we do to reduce the amount of blowholes or bug holes, as you call them in the States? I mean, it's a problem.
It is a problem. I think one would be, let's control the amount of water in the mixtures so that we've got less water available to move to the forms. Again, the right amount of vibration. Too much, you'll get honeycombing. Too little vibration, you won't get consolidation. It's a blackout. There's no simple answer to answer that. I do like Jeffrey's thought is maybe we need to be looking at the release soils. So yeah, there's no simple answer to that one, I'm afraid.
All right. Thank you, Grant, for your questions. And I want to end off by thanking Peter again. Thank you very much for taking the time early morning for you. We're going home after this, or I don't know, I am.
Yeah, I got to go to a faculty meeting. That's really great.
Well, thank you, and just give you one round of applause. Just say thank you very much for your time and spending it with us and sharing your knowledge. We look forward to that invitation of 1 year's feedback in 1 year's time. And we'll take you
All right.
up on that. And then
Okay.
we can talk about how it's progressed, or make it 2 years if you prefer. We'll see at the time. So,
And I'll see some of you in November. I'll be in Cape Town.
yes.
And feel free if you have any more questions. The society can forward them to me. So email.
Yeah, just contact Natasha and she can forward any questions that you might have. All right, thank you very much. I want to conclude the session and say thank you, and thank you for the presenter, organizer, and everybody that attended. Have a good evening and see you for the next event.